Welcome to the video lecture of Electronic Devices KEC 301. The unit that I will be discussing in this video is Unit 5, and the topic that will be discussed is MOSFET. In the previous video of the same unit, Unit 5, we have seen that what is MOS capacitor, and we have also seen the basic structure of MOSFET, that is metal oxide semiconductor field effect transistor. So this is the structure, that is cross-sectional view of enhancement type MOSFET. In the previous video, I told that we have the different types of the MOSFET, that we have an enhancement type MOSFET and a depletion type MOSFET. And in each of these categories, we have two more differentiation based on the doping. So we have four type of MOSFET: enhancement type N-channel MOSFET and enhancement type P-channel MOSFET. Similarly, we have depletion type N-channel MOSFET and depletion type P-channel MOSFETs. So this is the structure, the cross-sectional view of an N-channel enhancement type MOSFET, in which we have P-type of substrate, source and drain, and at the top we have the gate terminal. Between the substrate and the gate there is an oxide layer that is acting as an insulator between the gate and the substrate. Source and drain are heavily doped region, and as I have already discussed in previous videos that if we are having a p-type silicon substrate, then source will be of n-type and drain will also be of n-type, and these will be heavily doped. The gap between the source and drain is called as the channel length, and the lateral extension of this p-type substrate is called as channel width W. It is a four-terminal device having source, gate, drain, and body terminal as fourth terminal of the device. So let's see the operation of this MOS transistor. The carriers, that is electron in an NMOS transistor, enters the structure through the source contact and leave through drain and are subjected to the control of gate voltage. The substrate potential is kept lower than the other three terminal potentials to ensure that both p-n junctions are reverse biased initially. So taking the first case, when no gate bias is applied, means VGS is 0. Two back-to-back diodes exist in series between source and the drain. These diodes present current conduction. Due to these diodes, the current conduction is not allowed. It is prevented from drain to source when a voltage VDS is applied. So first case, let's see when we have VGS greater than 0 and VDS is 0. So when a small positive voltage is applied to the gate, the majority carriers, that are the holes in this p-type substrate, are repelled back into the substrate and depletion region is created. Since the surface is devoid of the mobile charge carrier, current conduction is not possible. So here comes a term, that is the threshold voltage, and we define the threshold voltage as a voltage at which the device will start conducting. So the threshold voltage is defined here as Vt is equal to Vt naught plus gamma under root minus 2 mod of minus 2 phi f plus Vsv minus 2 phi f, and gamma is the substrate bias or the body effect coefficient. Let VGS is further increased as soon as the surface potential in the channel region reaches minus 5 fp, surface inversion will take place and conducting N layers will form between source and drain diffusion region. The value of VGS at which conducting channel is formed is called the threshold voltage VTH. VTH is positive for N-channel FET and negative for P-channel FET. The gate and the channel region of the MOSFET form a parallel plate capacitor with the oxide layer acting as dielectric. The axis of VGS over VTH is termed as effective voltage or the overdrive voltage. So in this structure, the source voltage applied is 0 and the gate voltage that is greater than the threshold voltage is applied, and at the drain terminal we have a voltage that is equal to called as the saturation voltage. The saturation voltage is equal to or greater than the overdrive voltage, that is VGS minus VT. So when we apply a drain voltage around the saturation voltage, then the situation of pinch off occurs. Here we can see that the channel of the MOS transistor is getting tapered towards the drain terminal. Why this tapering of the channel is there? The channel is brought towards the source terminal and it is tapered towards the drain terminal. So here we can see between the source and the gate there is a potential difference of Vs is 0 and Vg is applied to some small positive value. If you see here between Vg and Vd, so this difference will be lesser to attract the negative charges from the surface, from the p-type substrate. So for that reason, the charges collected towards the side of source are more than that on the drain side, and here the depletion region is broader towards the drain side due to more reverse biasing at the drain terminal. So this situation, when the channel just touches the drain terminal and it is about to leave the connection between the drain and the channel, that voltage is called as VD saturation, and that voltage is greater than or equal to VGS minus VT. And this condition, when the channel just leaving of the drain side, is called the pinch off condition. Now this third diagram is showing the condition when we have applied a voltage at the drain terminal that is more positive than the saturation voltage. So if we keep on increasing this drain voltage, then what happens here, the depletion region gets wider and the channel is shifting towards the source terminal. You can see here there is no channel in this region. So in the concept that the channel is shifting towards source is a way of saying this. Actually what is happening, the channel is not shifting towards source, the channel is not existing here in this region. So we say that the channel is shifting towards the source. So the actual length of the channel that was initially between these two regions that we called as length L has now reduced to this value of L dash. Now this L dash is from here to here, and this effect on the channel length, that is reduction of the channel length, when we increase the drain voltage. So this reduction in the channel length due to the application of applied drain voltage beyond the saturation voltage is called the channel length modulation. This graph is showing the current voltage characteristics of the MOS transistor. On the x-axis we have VDS, that is drain to source voltage. On y-axis we have drain current. So here we can see that up to a point this with different values of VGS 3 volts, 4 volts and 5 volts. So these three curves are for different values of VGS. So here we can see as the drain voltage is being increased, the current is increasing up to certain value of the drain potential, and then it starts, actually it should start decreasing in a parabolic manner. But what actually happens, that if we find the maximum value of the current from the current equation, then we get a maximum value of current that is stable at this point. So that is the saturation current. It does not follows the parabolic path. After a certain point here, that is, we may call it the V saturation voltage, the current gets stable, and that condition and that current is called the saturation current. This will be the linear region and this will be the saturation region, saturation mode of operation of the device. So this graph is representing the same condition when the initially the drain current is increasing with the increasing in drain voltage. Then after reaching to a certain value of VDS, that is drain voltage, the current becomes constant. So if we find the maximum value of the current by differentiating the current equation and equating it to 0, then we get the maximum value of current that is constant and that is almost independent upon the drain voltage. Means we are increasing the drain voltage, but the current is now constant, it is not getting increased. This figure is defining the channel length modulation effect. In this, what I told you, that when we apply the drain to source voltage that is greater than the saturation voltage, then what happens, there is a modification in the channel length. The channel length is reduced by this value delta L here. Now the new channel length will be L minus delta L, and this is called the channel length modulation in any n-channel MOSFET that is operating in saturation region. This is the diagram that is representing the terminal voltages and the currents of the NMOS and PMOS transistors. So these are the two symbols. First one is for n-channel MOSFET and second is for a p-channel MOSFET. So here different voltages and currents are represented. Here we can see the current that is flowing in drain terminal is IT, and in the PMOS also we have IT current flowing into the drain terminal, and in the MOS transistor it is flowing out the drain terminal. So the voltages that is between drain to source is plus, that is VGS, gate to source is VGS, and source to body is VSB. Similarly, in PMOS, we have source to body voltage as VSB, gate to source voltage as VGS, and drain to source voltage as VDS, with the change in the polarity. Here you can see this VGS is actually VSG. So we can write it as VGS or we can write it as minus VGS. That will result to the plus VSG. Similarly, for VSB, we have VBS. Similarly, VDS is VSD. So, but the polarities are reversed for the PMOS, so the voltages are also in inverse polarities. These are the equation of current voltage equations of n-channel MOSFET. For if we have VGS less than VT means the device is not on, the control voltage is less than the threshold voltage, so at that time the current ID will be 0. When VGS increases and becomes greater than or equal to VT, then device is on. And in on device now we have two conditions, either it will be in linear mode of operation or in saturation. So first condition, current equation, that is showing the linear current equation. The linear current equation is defined as mu n Cox by W 2 mu n Cox by 2 multiplied by W by L 2 VGS minus VT multiplied by VTS and VTS square. So the linear current condition is VGS should be less than VGS minus VT. So if the drain voltage applied is less than VGS minus VT and VGS is greater than VT, then the device will operate in linear mode of operation and the current equation is defined like this. And the second mode of operation is saturation mode of operation. So when VGS is greater than or equal to VT and VDS is also greater than or equal to VGS minus VT, then we write the current equation as mu NCOX W by L VGS minus VT whole square 1 plus lambda VTS. Here this term is an additional term that defines the channel length modulation. And lambda is the channel length modulation coefficient. So if there is no channel length modulation effect into the device, then we can ignore this term because at that time this lambda value will be 0 if the device is not having channel length modulation effects. This is the current voltage equation of a p-channel MOSFET. In the similar way, here also if we have VGS greater than VT, then ID will be 0. So here, due to the reverse polarity, we have the threshold voltage negative for this MOS transistor. So if gate to source voltage is negative, then or 0, then only it can work. And if VGS is less than equal to VT and VDS is greater than VGS minus VT, then device will operate in linear mode of operation and the current equation will be given as mu P Cox by W by L multiplied by 2 VGS minus VT multiplied by VTS minus VTS square. The second mode of operation, that is saturation mode of operation, for that the condition of operation is VGS less than equal to VT and VDS less than VGS minus VT. And the current for the PMOS transistor in saturation mode of operation is given as mu P Cox by 2 W by L multiplied by VGS minus VT whole square 1 plus lambda VTS. So this term again here is defining channel length modulation. If channel length modulation is not there, then this term will become 0 because lambda will be 0 if there is no channel length modulation. Now we have depletion type MOSFET. I told you that depletion type MOSFET where the channel is already present. So we show a depletion type MOSFET by these symbols. The difference is that here you can see this gate side line is shown broader. So this broader line represents the already present channel between the source and drain regions. Now coming to a numerical problem with the knowledge that mu p is equal to 0.4 mu n, what must be the relative width of n channel and p channel devices if they are to have equal drain currents when operated in saturation mode with overdrive voltage of the same magnitude. How we can solve it? The two transistors are there. We have IDN is equal to IDP. The drain current of NMOS will be equal to drain current of PMOS. So writing the current equation, Kn dash by 2 multiplied by W by L into overdrive voltage. This VOV is called overdrive voltage. So VTS minus VT whole square is equal to Kp dash by 2 multiplied by Wp by L and VOV square. VOV is VGS minus VT whole square. So cancelling out some terms, 2L and VOV from left hand side and right hand side, we get this equation. And solving and simplifying this equation, we reach to this step mu n cux multiplied by Wn is equal to mu p cux Wp. And solving this mu n Wn multiplied by mu p Wp, we get the ratio of this mu p Wp upon Wn, mu n upon mu p as mu n 0.4 mu n, and that comes out to be 2.5. This is another numerical problem. An n-channel device has Kn dash is equal to 50 microamperes per volt square. Vt is equal to 0.8 volts and W by L is given as 20. The device is to operate as a switch for a small VTS. Utilizing a control voltage VGS in the range 0 volts to 5 volts, find the switch closure resistance RDS and closure voltage VDS obtained when VGS is equal to 5 volts and ID is equal to 1 milliamperes. Recalling that mu P is nearly equal to 0.4 mu N, what must W by N be for P-channel device that provides the same performance as the N-channel device in this application? So solving this question, the RDS is defined as we have V is equal to IR. So using this equation, we can find R as V by I. So V by I when we do, then V is our overdrive voltage, VGS minus VT. So in the denominator we have this VOV square, and in the numerator we have VOV, that is overdrive voltage. So this RDS, this come from here, R, that is V is this voltage VOV, and this is the current I. So V by I, so this VOV and this one get cancel out. So we get 1 upon Kn dash W by N VGS minus VT. So all the values, those are given in the prompt question. We put it here, 550 into 10 raised to the power minus 6 multiplied by 20. W by L value is given as 20. VGS is 5, VT is 0.8. So solving all this, we get 238 ohm, the value of RDS. Now we will calculate VTS. VTS will be ID into RDS, that we get as 1 into 10 raised to the power minus 3 multiplied by 238, and we get a value of 238 millivolts. So the ratio we can write as Wp upon Lp as 2.5 and Wl upon Nl as 50. So this was all about the MOS transistor. We have seen the working of N-channel enhancement type MOSFET, its characteristics. Then we have seen the symbolic representations of depletion type MOSFET and some of the numerical problems. Now in the next video I will be discussing about some remaining topics of unit 5 that are based upon the diodes, different type of photodiodes, solar cell. These all will be covered in the next video of this unit 5.